And if everybody's here, let me welcome our next speaker, Mr. Connor Zwick for Speak Easy on where artificial intelligence is going to eat after this. Welcome here, Connor.
All right, thanks. Hi, everyone. Okay, so today I'm going to be talking about artificial intelligence. Before I start, though, I want to make sure that we're on the same page about level, and I want to make sure that the talk's as relevant as possible. So I want to get a sense for the experience in the room. How many people here are familiar with programming, have some experience coding? Okay, so pretty fair number. Okay. What about experience with artificial intelligence? Like you feel like you generally know at least the high-level concepts. Okay, so a little bit less. Great. That's basically what I was expecting. So I'm going to assume that most people are basically, they've heard about the field and they're interested at a high level because they feel like it's this big trend that they've heard about and they want to learn more. And that's kind of what the talk's going to be geared towards. So my aim today is basically explain to you what AI is, explain to you how it works at a high level, explain what it's doing today, and then where it's going tomorrow. Quickly, though, to give you a little more context on me, my background is, my day job is I am co-founder and CEO of Speak. It's a startup in San Francisco. We basically build an AI English tutor. Think an English-speaking buddy for people that want to practice speaking English and become more fluent. That was spun out of AI research that I was doing before, which actually was rooted back in 2014. I was working on my last startup. It was called Flashcards Plus. It was the #1 education app in the App Store and had a few million users. And it was sold to Chegg. And I kind of found myself in a position where I was searching for my next thing. And I started to explore AI as a field, and I quickly developed a conviction that artificial intelligence was not only a trend of the future, but it was going to completely change the way the world worked in the similar way that software has up to this point. So one thing that, so artificial intelligence is a term that everyone has obviously heard of, and it's been around forever. But there's one problematic thing for this talk, which is the term artificial intelligence actually is very ambiguous. It means a million different things. So let's get on the same page. When I'm talking about artificial intelligence, AI, what I'm referring to is a specific branch of computer science known as artificial intelligence. And you can think of it as kind of any sort of task that tries to mimic the cognitive function that we normally associate with human thoughts. So examples of this would be like understanding language, perception, feeling emotion, planning, strategizing, those sorts of things. Those are abstract. In the real world, AI basically utilizes one of these cognitive functions to solve a specific task. So examples of that would be like chess. Chess involves reasoning. Therefore, if a computer plays chess, then that is an example of AI. Or driving a car requires perception, it requires planning. So if a car drives itself via software, that would be considered an example of AI. All of these things together, if you were to combine all of these different cognitive traits into one system, we would call that a human. That's what we are. If you combine all of those into a machine, we would call that artificial general intelligence. So that's AGI. That's the stuff that's in science fiction. That's like that's the stuff you see in the movies, you read in the books. It's like C-3PO from Star Wars, HAL 9000 from 2001: A Space Odyssey, that sort of thing. So that's like one bucket, and that's really hard. We might not even have any idea how to do it. We're not even sure that what we're doing right now will even is even possible to lead up to that. Though a lot of people think that current AI research is basically consists of the stepping stones to one day hopefully get to AGI, which is a very interesting future. In the meantime, though, what we're talking about is artificial narrow intelligence. And this is when you use a specific cognitive trait, or maybe a few of them, to solve a specific narrow task, right? So a computer that plays chess, or a car that drives itself, is a narrow artificial intelligent agent. And that's the difference between AGI and ANI. So whenever I'm talking about AI, unless I say otherwise, I'm talking about the narrow kind. And that's a kind that's like been studied for actually many decades. It's one common misconception about the field is that it's young. It's not. Artificial intelligence has been around basically since we had modern computers. And by modern computers, I just mean like a computer that's capable of doing functions electronically. I mean, there was significant AI research back in the 1950s. And I mean, we've basically always had this dream, as long as we've had computers. A good way to think about it, though, is that AI is more of a goal than an actual method, right? It's like a description of something that we want to achieve. But the actual way that we achieve it, that's like a subfield of AI. So over the last 50 years, people have tried many, many different things, many different ideas. In the 50s and 60s, everyone was all about trying to dissect the brain, understand how the brain worked, and then basically just like mimic it synapse for synapse. And then we were like, and then that just like proved way too hard. So then what was in vogue was something along the lines of, let's just like categorize everything in the world, every single object, and then let's map out the relationship between every single object. And then let's just like apply this logic on top, okay? And if we do enough work, then all of a sudden we're just gonna have this machine that just thinks like us, because that's all we're doing in our head. And that proved intractably hard. So we tried all these methods, and all of them were very promising theoretically, but they all led to very limited real-world success, and they were kind of discarded as pure, like, just a theory. And that has just been the story of AI for over 50 years, except for machine learning. So machine learning, you can think of it as a subset of artificial intelligence, just like all of the other things I just mentioned are. It's just another way about going to solve for artificial intelligence. The thing about machine learning, like the way to understand machine learning, is that instead of trying to program the artificial intelligence to be intelligent, right? Like give it a list of instructions or whatever. You design a system that can learn to solve the task for itself. So what does that actually mean? That means basically that if you think about it, a normal program, most people here, I would say the majority of people here have some familiarity with programming, it seemed. So for those that don't, like you can think of a normal program as essentially an explicit list of very basic instructions for computers to follow, because computers are very dumb and they interpret literally what you're talking about. Computers make no assumptions about how to achieve a task. Therefore, programming is literally like the art of programming is making very, very specific lists of instructions, and that is what programming is. This style of programming, though, it runs very contrary to most cognitive tasks, because cognition requires something called generalization. Okay, so a good way to think about generalization is to think about like the way that we do it, because we're the ideal cognition machine. So if you were asked to like look at a couch, or if you were to like asked to look at an object, and it was a chair, let's say, right? To determine what that object is, you don't go through a list in your head and say, well, that chair or that object has 4 legs, it is meant to be sat on, it has 2 armrests, and it's for one individual person, right? The way that you identify that that's a chair is you just like understand the essence of the chair. You have like an internal representation in your head of like what a chair means, and you can tell what the difference is between a chair and a couch. Even if the chair looks very different than other chairs, you still know that it's a chair. you've essentially internalized this essence, right? If I show you a brand new chair that is unlike any chair you've ever seen before, you immediately understand that that's a chair. No one needs to tell you, now add this to your definition of what a chair is. That's just like how the brain works, right? Machine learning tries to do something really similar, but this is why cognition tests in general are hard for traditional programs, because programs are rigid, right? And they're not very compatible with generalization, because you need to make these explicit lists of instructions, right? So a more concrete example is, let's pretend that we're trying to build a program to determine the difference between a 6 and an 8. So the programmers here, maybe if you've gotten into computer vision, you know, this was like an exercise maybe you had to do at some point. But how would you, if I asked you to create a set of instructions, right, to determine basically what the difference is between a 6 and an 8, right? Like write out to me a list of what the difference is between a 6 and an 8. How would you do that? Like, what criteria would you use to do it reliably so that any 6 you give or any 8 you give, the list of instructions tell you if it's a 6 or an 8? So common ideas would be, okay, so the 6 is, you know, a 6 has a tail at the top and the 8 has 2 loops, right? That would be like one way you describe it. But you can't just tell a program that. You need to do something far more basic. So maybe you would say, okay, well, we're going to count the number of pixels that are black, because an 8 requires more ink than a 6. And if you were to count all the pixels in an 8, on average, it would be much more than on the 6. So above a certain number of pixels, you know, it's an 8, and under a certain amount, it's a 6, right? Or maybe just like you count the top half, because the top half is the part that's the most different. But there's always edge cases. There's always something that breaks it. So here's an example, right? This 8 is very thin. This 6 is very thick, right? If you wrote a program that just counted the pixels, the 8 would be classified as a 6, and the 6 would be classified as an 8. And so you quickly realize that it's actually really hard to describe with a set of characteristics the difference between a 6 and an 8. Now imagine that you have to do that for all letters of the alphabet, and imagine that these digits can be, you know, rotated, and they can be skewed, and they can be transformed in many different ways. And as soon as you encounter any sort of novelty at all, let's say the 8 is like a particularly weird 8, the system breaks because you haven't accounted for that in your rules, right? So that is like the central challenge of generalization. Now, how does machine learning solve this? Essentially, what machine learning does is it approaches the problem in a completely different way. Instead of trying to describe how to perform the task with specific sets of instructions, you don't write any rules at all. What you do instead is you let the system learn the essence of what a 6 and an 8 is by just exposing it to many 6s and many 8s. And to do this, basically what you do is we call it training, and you train the machine learning algorithm by exposing it to a bunch of this data. And the magic of the machine learning algorithm is that it basically will become more and more accurate as you expose it to more of this data. In this case, we would feed it, you know, probably thousands of examples, and all the 6s would be different than all the 8s, because each one would be unique in its own way, which is why it's challenging. But if things go as planned, what should happen is as soon as you start training it, the system will become more and more accurate. Sometimes you'll get an example where the 6 will be, like, it'll look really like an 8, and the system will categorize it as an 8, right? And then we correct it, and we basically adjust the internal representation slightly, so that next time, it's less likely to miscategorize that one. And if you give it enough examples, it turns out that you basically can just build this internal representation with no rules specified. And then as soon as you give it a new one, you know, a weird 8 or a weird 6, it has the essence of the 6s and the 8s, and it's generalized, right? In a way that if you gave it a specific set of characterizations, it wouldn't. It's just like how we learn, right? It's just like how you conceived of a chair versus a couch. This is the exact same thing. You know, if you were to show a small child a bunch of pictures of like cars, each car being different, right? The child might walk out into the street and they see a brand new car, maybe a truck or something that didn't look anything like any of the pictures that they saw, but it was still a car, and that child will still recognize it as a car. That's how our brains work, and that's how machine learning works. So machine learning has actually been around and it's been effectively employed in a lot of problems, actually for several decades. But the thing that's really caused the hype of today's AI hype cycle is something called deep learning. And deep learning is, you can think of it as like a sub-task within machine learning, which is within artificial intelligence, right? So there are a lot of other techniques that are used effectively that is inside of the machine learning circle that is not inside of the deep learning circle. But everything changed basically in 2012. So 2012, all of a sudden people were trying deep learning, and it went from not working very well to all of a sudden just not only working, but like working unreasonably well. Like it broke all of the state-of-the-art records for a bunch of different problems: speech recognition, object recognition, handwriting detection, all like translation, all of these different problems. It started working in areas where machine learning couldn't even work and didn't even show any signs of working. Yeah, so I mean, what was so amazing about it was that you literally like, you didn't assume anything about the problem, and there were these researchers that had been working on deep learning for a very long time to no avail, and then all of a sudden, it started working for a reason I'll get into in a sec, and they were able to like literally go from like field to field that used to be dominated by people that studied this field particularly, like speech recognition, for example. There were people that like had PhDs in speech recognition and like studied for many years and built these complicated systems, and they would go and they would apply the same exact piece of software, like literally the same code that they use for like an object recognition competition and achieve state of the art, and they would take that same code, not modify it, and just use a different data set, and they would beat a speech recognition state of the art record. So it was an insane time, and people really didn't know what was happening. But to understand what deep learning is, you have to understand one more thing, which is basically what a neural network is. So neural networks they're not actually that complicated, but they're sufficiently complicated that it doesn't make sense for me to explain in great detail what they are in this talk. But at a really high level, the way that you can think about it is that it's basically inspired by the brain. It's a series of interconnected nodes where each node is basically like it's kind of like a neuron in your brain. Each neuron is responsible for a tiny part of the overall representation that we're talking about, right? And you can think of it as going like left to right. So you input, let's keep going with our example of the 6 or the 8, and you input it, and then it's passed through this thing called the hidden layer. And this hidden layer essentially does all these small calculations, but they're all interconnected. And the output is basically whatever result you want. And you basically just run tons of examples through this, and you train. And it turns out that this actually has a lot of capacity to learn. Now, one layer, you can only do like one set of transformation on it. So people started doing something called deep neural networks. And you'll recognize that this is kind of like the picture that I just showed you, but there's just like more layers of them. And that's because a deep neural network is literally just like one neural network, and then the output of one neural network is used as the input to the next neural network. And the next layer is put to the next one, and so forth, and you have many, many layers. And as you can see, it's hard to see in this example, but this is for face detection, and you can see that each layer, let's see if this works. Okay, so each of these corresponds to one layer. And you can see that this is like, these are like people's faces, and this is like the internal representation at that point. This is like, this layer is like looking for like details like eyes and stuff, and this is like looking for very basic like edges and stuff. And each layer kind of learns this representation, and it turns out that when you add more layers, you can do really, really complicated and sophisticated things. And so the question is like, why did no one try this? Get this water. Right, so why did no one try doing this deep neural network before? And it turns out actually people did. People tried this in the 80s, this exact same concept. The thing is, a single layer network, that's been around since the 50s, but that is very, very complicated math. And in the 80s, you could barely do one layer. And as you add more layers, it gets exponentially more complicated. and it becomes much, much harder to train. You basically are optimizing like this huge, huge math equation, and it was too much compute. It was just far too complicated for people in the 80s to solve. So the process of training it, they tried. It was intractably hard. They were training really, really tiny models. They tried it, the results weren't great, and they were like, this is just like everything else, it doesn't work. We'll put it away, we'll try something else. And then something happened. And this is what happened in 2012. It kind of happened before that, but 2012 is really like when the tide turned. So in 2012, two things happened, or two trends led up to this revolution. And the first trend was that there was the internet, and all of a sudden there were these really big tech companies that were making a lot of money and were collecting user data from many millions of users. They were collecting audio, they were collecting images, they were collecting text, right? Google was collecting search queries, Facebook was collecting statuses, etc. That was one trend. On the other side, you had companies like NVIDIA that were building GPUs. For those that don't know, GPUs are basically like the graphic computers inside of your computer. And it was almost entirely fueled by the computer game industry, basically just better graphics for video games. So these two things kind of were happening in parallel. And around 2012, a lot of these tech companies were like, let's try these deep neural networks again. Let's just try training, but we'll try training much larger ones, because now we have the compute for it. And since it's much larger, it turns out you need a lot more data for it. So they had these massive data sets of user info that they had collected from their millions of users. And this is basically what revolutionized it, because it turned out that the missing part was just that you needed really, really big models, and you needed lots and lots of data, like way more than people had tried before. Oops. So this graph is from Baidu, and it's an interesting graph, and it shows a pretty interesting point. So basically what happened was, on the y-axis you have performance, and on the x-axis you have the amount of data. So the red line is basically like traditional machine learning, and the blue line is deep learning. And what you see is that it turns out that in the beginning, when you have, let's say you have 1,000 points of data, right? Both algorithms like work about the same. Deep learning is a lot harder to calculate, so no one does it, right? Because it's way more computation than the other algorithm. They achieve the same thing. But when you have like 5,000, then 5,000 data points, the other machine learning algorithm, it gets better because you have more data. And then let's say you get a 10,000, and at 10,000 it starts to peter out a little bit. It's plateauing. And if you do 10,000 and then 20,000, 40,000, 100,000, you can just throw more data on it, and it's not going to go anywhere. It's like peaked out, and that's basically was the state of machine learning. However, with deep learning, what happened was it didn't plateau. You would add more data, and it would just get better, just a little bit. And then you would add more data, and it would get better, just a little bit. And you would add more data, and it would get better, not a lot, just a little bit. And but it didn't plateau. And that was the crazy thing. So all of a sudden, all of the data sets that academics have been training on and everyone had been training on for machine learning algorithms up to that point, they were too small. They were way, way, way too small. And so the only people that could train, the people that were making progress in deep learning, it was literally just like all about if you were good at getting a unique data set that no one else got, and then training on it and experimenting on it. And then you would achieve some new result, you'd write a paper, and you become really well known in the community. And that is how all the progress in deep learning has happened for the last few years. I mean, people have made other changes, but that is the key. The key has always been data. It's actually a very common misconception. So a lot of people think, oh, well, we made some breakthrough with the algorithm. We thought of some new idea. But no, these ideas have been around for many decades. The algorithms that the breakthroughs were made on were not novel in any way. At this point, we've definitely improved, and all of those things are getting better. But they happened as a result of having lots of data to train on, which allowed you to essentially guess and check. We don't have that theoretical understanding because it's too complicated. It's just like too large of a math equation. So a common phrase is it's a black box. Everyone basically just says that neural networks are a black box. We don't understand why they work so well, but they do. And any algorithm improvement has been a result of someone having an intuition of like, what if we just tried to do it this way instead of this way? I'll try it, and then it didn't work, and they tried that 10 times. One time it worked, and then they did that, and then they tried 10 things similar to that, and it worked a little bit better. And that's like how all the algorithmic progress has been made. So I think the moral of the story there is basically just like, the entire revolution around AI has been completely centered around data, and that is like of paramount importance. Okay, so fast forward to today. We're at peak AI hype. It's only really going up. These are like basically just Google search terms for machine learning, artificial intelligence, deep learning, right? Like over the last 5 years since the initial deep learning paper that changed everything came out. And so, we've got all of these AI researchers working for Google and Facebook that are literally getting paid millions of dollars a year. We've got venture capitalists investing 10x more in artificial. Everyone in Silicon Valley is doing an AI startup now. It's peak hype, and a lot of people are saying that there's like this AI bubble, right? People have unreasonably high expectations, and there's no way that we'll ever reach those expectations. So I think all of that is true, and I think it definitely is overhyped, and there's a lot of froth to the market. But what I would say, and I think one of the biggest points that I'm trying to convey, is that there is like real progress being made here that's extremely valuable, and it's already happening today. So I'll give you a few examples of how deep learning has been implemented in commercial products that are live today, that are like changing the game. So speech recognition was one of the first things that deep learning revolutionized. We weren't very good at speech recognition, and then all of a sudden, we were really, really good at speech recognition. In a few more years, we'll be human level at speech recognition. It might even be sooner than that. Speech recognition for most people is faster than typing at this point, especially on mobile devices, because of the accuracy. It's created an entire new industry in smart speakers. You have Alexa, you have Google Home, all of that stuff. And it's proving to be a new human-computer interface. Like the only human-computer interface we really have right now is just keyboard, mouse, and touchscreen right now. And voice is this new one that is like all of a sudden taking off. And the only reason it's taking off is because of the accuracy of speech recognition, all because of deep learning. Object recognition. So object recognition is just literally like being able to interpret an image and detect objects in it. This has already been implemented in Google Image Search. So you can search for a particular image, and it can recognize faces, and it can recognize objects in it. Before it required tagging. This image is basically Pinterest. They have a visual search. So you can click on an image, and then if it's like a vase or something, you can see other pictures of the same exact vase that other people have taken photos of. And most importantly, you can buy the vase, which is central to Pinterest's monetization strategy and how they're going to make all of their money. Again, only possible through deep learning. Another example, smart replies. So if you guys use Gmail, you might have noticed on your mobile app that there's this suggestion box at the bottom with a few suggested replies. This is basically just Gmail using deep learning to automatically guess what you're going to say. And guess what? Over 10% of all replies sent on Gmail's mobile apps use smart replies to respond. So over 1 out of 10 responses that people send on mobile apps are automatically generated. And mobile is only a small part of the total, but in aggregate, people send hundreds of billions of emails a day. So if even a small percentage of those emails are automated, you're saving a lot of time around the entire world. All of these examples are of products that were literally impossible 4 years ago, that have gone from impossible to in commercial products that are hugely important in less than 4 years. And this is truly just the tip of the iceberg. This is the beginning of the cycle of a new technology trend. This is the equivalent of 1980 for normal software, right? All of the really exciting stuff is still to come. So my thesis, and I think it's a really great way to think about artificial intelligence, And if you're trying to figure out how it applies to your field of interest, these are 3 good principles for thinking about and predicting how AI will impact whatever you're interested in. So the first one is AI can add value by making things cheaper. So it can make things that are expensive and valuable today super, super cheap, orders of magnitude cheaper. The second one is it can make humans more effective, which is in itself very valuable. And the third one is that AI can sometimes do things that humans can't do. It can make the impossible possible. And I like to use these 3 points to evaluate if there's, if I'm trying to think about, well, how could AI touch this field? I think about these 3 points. And I'll give you a few examples of each. So the first one is just making things cheaper. This is like by far the most obvious one, and the way that has the most obvious value. So just one example is it makes products get to your doorstep, and it makes them much cheaper. Amazon, as probably all of you have heard, is doing drone delivery. That means like literally taking the package and like dropping it off in front of your doorstep, deep learning. Uber acquired Otto for hundreds of millions of dollars. Otto is a autonomous truck delivery company, which will be the future of all transport across land. As you can imagine, like if you don't have to pay drivers to do any of that, products become much cheaper. Not to mention robots that are building more and more of the products completely autonomously. All of that is going to be continue to get more and more automated. Another example is language translation. So language translation used to be, Google Translate used to be terrible, and now it's entirely powered by deep learning, and it's actually become quite good. And most people agree that it will become better than humans in a few more years. And better than humans in a lot of ways. I mean, it'll be almost free, it'll be instant, and in many ways it'll be superior. And translation alone is a $35 billion industry, and it will be completely replaced, if not almost completely replaced by humans within the next 10 years. That's almost for sure going to happen. Okay, the second one is making humans more effective. So there are many, many examples here. One is just better search. Google has incorporated deep learning heavily into the way that their algorithms work. All search companies have. But you also have other sorts of search that before seemed impossible. For example, face recognition. Now you can search and very quickly see pictures of maybe your friend, and you can just see all the pictures you've taken with them. Or you can like search through maybe a video of me speaking, and you would be able to search for like that moment when I said that one thing, because there's a transcript that they can just search, all powered through deep learning. So search just saves people time, and you can search things that you weren't able to do before. You can imagine lawyers being able to search through case studies and through precedents very, very quickly in a way that they can't right now. Generating content. The Associated Press and Wall Street Journal, they generate a lot of articles now, completely by machine. Sports articles and financial articles in particular. And these articles are just as popular as the rest of their articles. Summarizing and understanding text. If you're a researcher and you want to understand a specific concept and you need to read 20 research papers to get to the top of the field, you can have an algorithm just summarize the papers for you. These tools already exist, and they're only getting better. One side note here is something called human in the loop. It's actually a pretty interesting phenomenon. It's many, many new AI companies are this model called human in the loop. So if you haven't heard of human in the loop, it's very interesting. I'll use my friend's company as an example. So they're trying to automate virtual assistants, specifically for like scheduling and coordinating meetings. That problem is not solvable by AI today, but it will be if you had enough data. The problem is the training data is really, really hard to get. So what do? Well, they have an algorithm that works 85%, but you can't commercialize a virtual assistant product that works 85% of the time because you still need to read through all the emails. What you can do, though, is you can hire virtual assistants, have them review them, which takes a lot less time than writing the emails, and then now all of a sudden you need one virtual assistant where before you needed 10. And that's what they do. They offer a virtual assistant for a price point that's 10% of what a normal virtual assistant costs. But guess what? What their secret plan is to be generating this giant data set that they're literally getting paid to create, to one day remove the humans altogether from the equation. So in the short term, it's making humans more effective, but in the long term, it'll make a product just dramatically cheaper. The third thing is kind of interesting for a different reason, which is that sometimes there are things that humans can't do. And there are a few different very common scenarios here that a lot of startups are exploiting, including myself. So the first one is just humans cannot handle monotony. We're very bad at doing repetitive, boring tasks over and over again. There are a plethora of security camera startups that are all using deep learning because if you pay a human to watch a bunch of security cameras, that human they'll nap, they will not pay attention to all the threats that they should be. They might not even be able to identify all the threats. However, deep learning is able to do face recognition. So it's able to identify who every single person is. It's able to know if that person is in the company database and is an employee, or if they're likely an intruder. It's able to do things like detect other objects that pass through the screen really quickly that a human might not catch. It's 100% vigilant. It never falls asleep. And it can watch as many cameras as you want for free. Another example is things that are too complex. As a human, we can only hold a certain amount of things in our brain at once. This is actually really troublesome for a lot of industries, but financial trading is a huge one. Wall Street trader, or any financial trader, a lot of the decisions they're making on what to buy and what to sell, that's entirely a human judgment call, filled with bias and lack of knowledge. But a machine can be trained to do none of that. And in fact, there are many hedge funds today that use AI to generate higher profits, like many. And of course, these things will only become much better over time as they get more training data. The last one that is interesting is sometimes humans are just too human. They have emotions, they're judgmental, and sometimes it's just embarrassing to interface with a human for certain things. There are a bunch of startups that have started basically offering therapy in the form of a texting bot. And it turns out that this is like scientifically proven to be actually quite effective at treating things like anxiety and depression. And it's a really good first step for a lot of people that would never go to a therapist otherwise. So it's clear that AI is going to be this huge force multiplier. One really interesting question in this space that I would pose to you guys to think about, but I think it's just generally interesting, is the question of, in the future, will all this value that clearly will be created, will it be all captured by large companies, right? I mean, like Google and Facebook and Baidu and Naver, they all have all the compute. They've hired the best deep learning specialists in the world, and they have all the data, right? So will they capture everything? And I think Comma.ai is a very interesting counterexample. So for those that have not heard of Comma.ai, it was a startup created by George Hotz. He's the guy who first jailbroke the iPhone like 9 years ago. So basically what he did was he used open source software and he built a self-driving car in like 4 months by himself, no help. Meanwhile, like GM and Google and all of these other companies have like huge teams. He built a self-driving car by himself. And he did it because deep learning is actually like it doesn't actually require a lot of lines of code. It just requires being crafty with how you train. And he was able to figure it out and build something really effective. And he was a one-man shop at that point. He has since gone on to raise a lot of money from a lot of prominent venture capitalists. But that is food for thought for why an individual player, there's a lot of room for individual players to come in with a unique idea, especially around how to train, and figure out one of those 3 areas that they'll do, right? They'll either make something cheaper, they'll augment the human, or they'll just make something possible that wasn't possible. And I think that will happen a lot. In fact, I think it's very clear that there will be a lot of AI startups. I mean, there already are a lot of AI startups that are like quite new, and the space is already full of them. But I think you will see a very common pattern. I think there are companies that are very young right now that will be worth $1 billion or more in only a few years that are doing AI, that are very, very novel right now, and you haven't heard of them yet, nor have I, nor has anyone. But what they'll do is they'll follow this similar arc that a lot of companies that end up being worth a lot in the AI space will do. which is they'll identify some sort of problem that they can either make really cheap with AI or augment a human job, or make it impossible. And then what they'll do is they will figure out how to collect some sort of data set in order to train their algorithm. And they'll be able to, and they'll probably have to be like really crafty there, because if it's obvious, then someone else would have already done it. The challenge is there's a lot of things where you're like, when you're thinking about AI startups, there's a lot of times where you think of like, oh, well, AI definitely could be capable of this if we had a data set. But the question is usually like how to get the data set. So then you figure out how to hack the data set. And then essentially from there, you use the data to train your algorithm and create the value add, create the product. People find value out of it, they use it, you generate more data, you use that data to create a better experience. The hedge fund becomes more accurate with more data. The self-driving car becomes more accurate as it drives more miles, et cetera. And that eventually just loops around such that you have a moat of defensibility around your data. And eventually it gets to the point where it's too hard for competitors to even try to replicate what we've done, because their experience that they can build with the data that they're able to get is just like not even comparable. So I'm conscious of the fact that I sound very, very optimistic, like unreasonably optimistic about this. So I want to cover like all the shortcomings and all the challenges, and cover both sides of it. So I think there are a few challenges that everyone agrees we need to figure out. So one is like the hype. There's a lot of people that are very optimistic, but they don't really understand how the technology works or what they're doing. There are a lot of startups that are working on a problem that's not solvable. There are a lot of venture capitalists funding ideas that probably should not get funded, but they don't understand the space well enough to evaluate that. Another one is that we just generally don't know the theory, like I was saying earlier. And it's actually a bigger problem than it sounds like, because there are things that fall out of that. As an example, here's a picture of a panda, and a normal object recognition algorithm with 60% confidence identifies it as a panda, right? Pretty straightforward. Then you apply this layer on top of this image. You basically apply it, and then it becomes invisible. And this image on the right, with the same object recognition, has a 99% confidence that that image is a monkey instead of a panda. And that was basically engineered. And that in itself doesn't seem like a big problem. But what about when there are autonomous cars that are driving around, and a hacker figures out, like reverses some sort of, like maybe Google is doing their self-driving cars, and they figure out that they can paint a certain QR code on the side of a building, and when any car drives past it, they just like veer off the road and crash, right? This is like an example of an adversarial example, and right now we have no clue how to fix it, because we don't understand what's happening inside of the neural network. So all of these are examples, but I think they're all, these are all shortcomings, but I think they're also things that are very solvable. Like like currently a lot of people are working on this exact problem, and I think it very clearly will get solved. And I think the ultimate question is more basically just, how is this going to actually change the world, in which ways? And again, I think you use the 3 different ways that it can add value, and that's a very useful way to evaluate. But as far as the question of like, how far is this going to go? What is it all going to change? I think there's actually a very simple answer to that. And I'm going to leave you with that. It's basically this graph. So this is a graph of basically NVIDIA's GPU. And there's a green line. It's a little faint on the screen. But this is basically starting in 2000 to 2014. And you see the compute power and you see the way it's going. People are working on quantum computing, which will make this even crazier. But the compute that was possible in 2014 allowed self-driving cars to be possible. That was impossible in 2006. Like, we just literally did not have the compute to do it, and we do in 2014, right? Imagine what this graph looks like 10 more years if this progress continues. What is impossible today that will be possible in 10 years? What will be possible 10 years after that, assuming that our compute continues to increase, and assuming that we have a continuation of more and more data via sensors, Internet of Things, people using the internet more, mobile phones, et cetera, right? That's an unknowable question, but I think it's very clear that this is very powerful. And as you get more compute and you get more data, more and more things become possible. So yeah, that's pretty much it. Thank you, and if you guys have any specific questions, I'd love to answer them.
Thank you, Connor. We're now open for questions from the floor. Is there any questions out there from you? Anyone, just raise your hands. I'll bring the mic over.
Yeah, hi. Thanks for the great speech, great talk. So I'm actually a mobile software developer. I build mobile apps. I was wondering, like, I've done some online courses, but what's a good way to actually get deep into deep learning, I guess? Or
Just like learn more about it?
yeah. Well, do you have any resources or stuff like that that you can recommend?
Yeah, there's a ton actually out. Coursera, if you're familiar with Coursera,
Yep.
has a really good introduction to artificial intelligence course.
Yep.
That was just revamped. I would recommend starting with that.
All right.
It's actually a surprisingly shallow field. Like as I said, I spent 18 months going from zero to being able to implement a lot.
Is that the Andrew Ng one?
Yes, that's the Andrew Ng one, yeah.
All right.
He's revamping all the content, yeah.
All right. Thank you.
Anyone else?
Good afternoon. Just question on the trend how the deep learning is going. I see that the way how, because of the processors and also the big data, capability data, and how the deep learning is coming is like study the data and the pattern of data. But if you look at how is the deep learning is going, does it really emulating how the human brain power is behaving? Because I see there is still very big gap in how the deep learning trends. What is your thought on that?
So the question is basically, how close is it actually to a human?
Right.
Yeah. Well, I think there are two different ways of thinking about it. One is, how close are we to somehow getting to the point where we have like that AGI that I was talking about? And the other is just like, how are we close with compute? And so I think the first is a very unknowable answer. Like, we don't really know. And generally, like when we solve some sort of task that we thought would require strong AI, and then we solve it, we just basically are like, okay, that is no longer AI. And like, there's a new standard. In terms of compute, we're still many orders of magnitude away from the compute of one human brain. Like, collectively, all compute in the world is not even close to the compute of one human brain. But if Moore's law continues, which is very unclear if it will, in most of our lifetimes, we'll get to the point where we'll have, not like 10x, but like 1,000x, 10,000x as much compute as we do now, compute capacity. And I think then, that's like, my personal opinion is that the way that you get to human level AI is by having a really, really big network that's about the same size as the brain. And then just exposing it to things.
Hi, my name is Stacy. I'm from TradeMe. Just a question related about, because I'm not really sure AI or this, but in the general travel industry, do you have any, in your mind, like any company or any tools that they are using this to make the travel experience better?
Are you asking about the travel, like
just basically on in travel industry?
Booking travel as well?
Any company or any tools that you think
people,
they can?
yeah, people are using it for predicting when you should buy airline tickets. They're using it for like optimizing routes. In terms of the experience while you're traveling, it's a little bit harder of a question for me to answer because I'm not very familiar with the travel industry. Though I do think like the number 3 reason that AI impacts what we're like making the impossible possible, that I think is really interesting because it's like in 2008 when the iPhone came out, people created all of like the apps that were like basically just a version of something that was happening in the real world, right? And that was like the first generation of apps. Like I made an app that was just like a flashcard app, and it was like a virtual flashcard. And it took like a few years before people started creating apps that really like took advantage of what was now possible that wasn't possible before. So you have an app like Uber. That wasn't really possible over smartphones, but yet it took like 4 years after the iPhone had come out before someone like actually implemented that and turned it into an enterprise. I think it's similar here. There are many things that we're just not thinking about that are like second order and third order effects of the capabilities of AI. And those are the things that, if you think of it, you'll have some sort of, you'll be able to create a big company out of.
It's okay. I'll go to the one at the back, and we'll go to the next. You two.
Hello, I'm Chiu. I understand that your company is doing apps that doing some form of the teaching for people to learn English, speak English. So I understand this type of apps, like if you want to have this type of functionality, the speech recognition will need to be very accurate,
Yes.
maybe near to 100%. But I understand currently, based on current technology, in terms of speech recognition, even people like Alexa or Google Assistant, their recognition rate is limited, especially when you deal with accent. So how do you make your apps very accurate to be near 100%, even surpassing those of Alexa or Google Assistant or other companies?
You mean specifically
In terms
like,
of speech recognition rate.
For someone learning that might have an accent?
Yes.
Yeah, totally. So it turns out for speech recognition, a huge problem is that like accuracy rates are pretty high for native speakers in a quiet room, but as soon as you get in like a noisy subway or you are trying to recognize speech from someone that has a heavy accent that's non-native, accuracy goes way down. So what we're building is speech rec for people with accents that's like much more accurate. And the way that we're doing it is we basically are collecting the largest data set in the world of aligned like speech data from people that are speaking with accents that's labeled. And we have a huge data set. We have over 100,000 hours of people speaking, and we basically use that to train. And so we figure out a hack for collecting that data. Well, you asked if they have the same similar sort of data set, and they actually it turns out that they actually don't have enough accent data because people with accents can't use Alexa or Siri because the output isn't accurate enough to do anything valuable, so no one speaks into it. And they also need to transcribe it. So they actually, it turns out they don't have a lot, or not enough to do anything interesting.
Hi, I'm Prem. I'm working on machine learning as well.
Oh, cool.
So as a developer, I face a lot of problem in terms of getting data.
Yeah.
So what's your advice? For example, there are a lot of open data available that I can get. But for example, if I want to predict some human behavior, that data belongs to, a lot of data comes from Facebook or from Google, and it's very expensive for me to get some. And where do you think I can get my own data? Do I create my own IoT thingy for me to get the data, or how do you do it?
I mean, that is the $1 million question. That's kind of what I meant with algorithms don't matter. It's all about, especially if you're working on something that requires machine learning and you need that unique data set, and you know that you could do something really interesting if you had the data, but you don't have the data. That's the conundrum that most people don't get past. And I think there's not a one answer for everything. It totally depends. So for example, for us, we built an app that people speak into, and we basically tell them what to say. And it's more of a niche app. It's not as good as the app that we eventually want to build. But it was good enough that we still were able to have hundreds of thousands of people using it and basically voluntarily providing their data, and we were like, they would just like read out the transcript, right? And so like we came up with that hack, but I think it's like, without knowing more, it's just, there are like a million different things you can do for a million different problems. And a lot of them are just like, some things are just impossible.
Exactly, it's like the time it takes to reach 100,000, so
Yeah.
that's another thing, right? So,
The human in the loop approach is really interesting though, right? So a lot of people do that, and I think that's a really good hack.
Just another question. As a developer as well, I would like to know, when will we reach a point where law firms, start coming to machine learning developers, because they are like, we are stereotyping in a way, and like for example, there's like classification problems, right? And even if you develop a solution and that solution fails or something, so where are we in terms of,
You just mean like legal precedent?
Yeah.
Anyone that I know that's in law school right now, I tell them to go into, to study artificial intelligence as well, because I think that there are a million interesting legal questions that are completely unsolved, and these are all going to be litigated in like very high attention court cases over the next few decades. Like, there are just so many questions. For example, like if you train something on a public data set, or on a data set that is, maybe you don't actually have the rights to commercialize, then what happens when you that resulting algorithm you commercialize? Does that count as part of the process? I mean, that's just like one example out of many. I'm not a lawyer, but that's like, I think there are tons of interesting legal questions that need to be battled out in court, and I have no clue where they will go. I also think a lot of people are trying to regulate the AI industry because they're afraid of like these existential threats. A lot of people think of it in the same way that they think of like nuclear bombs, where they think that there's like this potential for bad actors to use it in really, really bad ways. There's already evidence that people are using AI to build really, really big botnets, for example, to crash websites, and there's a ton. Yeah, if anyone's a lawyer, you should study AI.
Shall we make this the last one then?
How do you see, because we have all the big tech titans like Google or Facebook, dominating the AI industry. Do you think there's still space for startups to actually innovate in this industry? Because Facebook and Google, they have the capital, they have the best talents, they have the flexibility to mobilize. So what do you think about what's the feasibility of them dominating the market, or what are the chances for startups to still be able to,
Yeah, well, I mean, that's kind of what I was covering earlier with the comma.ai self-driving car startup. I think there's a lot of people that think that it's going to just be dominated by these big companies, especially when you have like Google, where like Sundar Pichai went on stage a few days ago for Google I/O and was like, we're reaffirming that AI is the future of Google, and we're like doubling down. And I was talking with a New York Times reporter a few days ago, and he was coming out with a story recently, or he's gonna come out with a story where basically like these AI researchers are getting paid literally millions of dollars at companies like Google. So they're just throwing money at the problem, and it's a good way to dominate an industry. But I think that there are still, I know countless people that are working on AI startups, and I think there's a very solid chance that, for either it's not an industry that's interesting to the Googles of the world, or they have some sort of hack for getting the data. Like, I think we have a really good hack, my company, and I don't think Google will be able to replicate it. And I think there will be just a lot of upstarts like that. And a lot of them might just end up getting acquired for, hundreds of millions of dollars, right? But that still is like a reason to start it. Yeah.
All right, thank you. So I think we've come to the end of the session and also the end of the day. Thank you so much, Connor, for making time to share and answer all the questions today. And thank you to every one of you here for making time to come and learn. And if you've got your feedback survey, just drop them off. You might win some prizes out there. Thank you again, and hope to see you again.